Good evening, folks. Welcome back. This is Mike coming at you with yet another video on foundations of mathematics DOS. In this video, we are going to take another fairly large jump here. It is related to what we talked about in the previous couple of videos. We are going to be talking about lines, but we're going to be talking about lines in a little bit of a different context. So let's get right into it. Sometimes we have two quantities that can appear to have a relationship between them. Sometimes this relationship is a little bit more obvious, like say the number of units of a product you sell and the quantity of profit that you have, and maybe in some cases, the two quantities may not appear to have as obvious of a relationship. But we do want to test, in many cases, we do want to test to see if those two quantities may have some kind of a relationship. So if we have two quantities, x and y, we can test to see if there is a relationship between the two, and we test with a method known as regression analysis, and particularly we are going to focus on a linear regression. We're going to see if there's a linear relationship between these two quantities, x and y. Now, when we do this, when we test to see if there is a linear relationship between x and y, we're going to test this potential relationship given several pieces of information, given several ordered pairs that we're going to use. So we may have n ordered pairs, x1, y1, x2, y2, x3, y3, all the way up to and including xn, yn. And if we want to see if there is truly a linear relationship between these two quantities, x and y, we have a calculation and we have a particular number that allows us to measure how close x and y are to having a linear relationship, and that number is called the correlation coefficient. My apologies there, guys. The correlation coefficient tells us how strong of a linear relationship that the two quantities x and y have. Now, they can have a positive linear relationship, which says that as one goes up, so does the other. They could also have a negative linear relationship, which is as one goes up, the other one goes down. So here are just some sketches of some of the cases we could have. The first two here, these are examples where the data points exhibit a strong or just some kind of positive linear relationship. Each of these dots here shows us our data point, one of these guys here. And in this one here, we see that all these data points are very, very close to each other. They're very, very close. And if you picture drawing a line through here, drawing this line here in pencil, if you picture that line being drawn, we see that these these points here, my apologies once again, these points here are all very, very close to that line. It's not missing it by that much. So this would be an example of a strong positive linear relationship. These two quantities, x and y, if you look at their points, they almost form a perfect line. Here on the right, we have an example of a weak positive linear relationship. If I were to sketch a line through here, then yes, the points are not perhaps super far off from where this line is, but they are a lot farther off than what they were from the graph at the left here. So this is an example of a weaker positive linear relationship between these two quantities, x and y. The bottom two here are examples of negative linear relationships. The one at the left here is an example of a weak negative linear relationship. The line that's going to sort of best fit this set of data or these data points, and we'll get back to this idea of a best fit line in just a little bit. We see that these data points are perhaps not super far off from where this line is, but they're kind of far off. They don't line up very well to give us a nice clear line. But overall, these data points are trending in a downward fashion. So this is what lets us say that this is a weak negative linear relationship. And then over here at the right, we have a strong negative linear relationship. If you picture this line, that sort of best fits or sort of goes in with where all of the data is. All these data points are closer to forming a nice perfect line. These points aren't very far off from this very crudely drawn line, which I put here. So this is an example of a strong negative linear relationship. On the back here, this graph right here is an example of something where there's not necessarily a clear relationship between the two quantities x and y. The points are just sort of all over the place. There's really no clear line here. There's just really no linear relationship between these two quantities, x and y, whatsoever. Now, this correlation coefficient that we call r is always going to be a number between or equal to -1 and +1. If r is equal to -1, then you have what's known as a perfect negative linear relationship. That would be where all of your points form a perfect line with a negative slope, and all those points lie directly on that line. If your r value was a +1, you would have an example of a perfect positive linear relationship between those two quantities. You have a line with positive slope, and all the points, all the data points, would lie on that line. Now, we do have a formula for calculating this coefficient r. Fair warning, this is an ugly looking formula. There are going to be some separate calculations that we'll have to do and some perhaps fairly large numbers that we will be working with, but we're going to try to keep the sample problems here not too bad. If we have to calculate the correlation coefficient for a set of data, it's given by this formula right here. R is equal to, let's get into what all these symbols are. N is the number of data points or data pairs that you have. Now you see this fancy looking capital E thing. It looks really weird. This is the capital Greek letter sigma, and we typically use this capital Greek letter when we're going to be taking the sum of things, when we're adding things up. Now this is the sum of, or sigma of, xy, x times y. And here you can see sigma xy is the sum of the products of the x and y values for each pair. Still on top, we have minus the sum of the x values times the sum of the y values down here. That's the entire top of this fraction. On the bottom, we have the square root of n times the sum of x squared. So what we're going to do in that case, it's the sum of the squares of the x values. So we're going to take each x value, we're going to square that, we're going to square each of those, but then we're going to add those up. And that's what this guy is here. So it's that minus sigma of x, that number squared, times the quantity, n times sigma of y squared. So take the y values, square them, add those up, and then minus sigma of y squared. That is very ugly. We're only going to be doing sample problems here where we're working with very few data pairs. So there's not a whole lot of calculation that we're going to have to do, and we're going to organize all this information. We're going to calculate each of these various pieces separately, and we're going to label them out nicely so that we can easily identify each thing, and then we're going to nicely plug them in. Yes, the calculations will be ugly, but here is where we can do our correlation coefficient. So, great. We can find this correlation coefficient. Fantastic. We're going to get some number between or equal to -1 and 1. But what does that really tell us? Well, based on what your R value is, based on how close it is to +1, or how close it is to a -1, that can actually tell us how certain we can be that there truly is a linear relationship of some sort between the two quantities x and y. And what's sort of the magic number here? If I look at table 11.4, these are copied right from the notes. So we can see here that we have various sample sizes. So various numbers of data points or various values of n, looking at the formula that we just looked at. And then we see this 5% column or this 1% column. And we see that based on what sample size you have, we see that as you add more guys into your sample, the numbers in this 5% and 1% columns, those numbers go down. So here's where we're tying this chart into when do we know, or when can we be reasonably sure that there is indeed a linear relationship between x and y. If when you calculate your correlation coefficient, if the absolute value of r is greater than or equal to the value given in this table here, for either the 5% column or the 1% column, also known as the 5% significance level and 1% significance level, then we can reasonably conclude that the two data sets are indeed linearly related and that there is a linear relationship between those two sets of, or between those two quantities, x and y. That may seem like a whole bunch of information that was just thrown at you. Yes, it can be a tad bit confusing, but we're going to do sample questions here where we see and where we'll actually use this table and figure out what does this actually mean. So for now, this is just a metric. This is just a rule that we're just being introduced to right now, we're just trying to sort of get our feet wet with this. We'll really start going into the deeper end in the next video when we do some practice problems here. So we find this R value, we find this correlation coefficient. Perhaps we find out that it is that there is indeed a linear relationship between these two quantities, x and y. Okay, that's fantastic. But what is the model that we can use to actually relate these two quantities, x and y? And earlier on, I talked about creating a line that sort of best fits these pieces of data that were given in each of these 4 cases here, and then the 5th case on the back. So that line that sort of best fits the given points of data that we have is sometimes referred to as the least squares regression line, but we're just going to call it the regression line. It's going to be something that is in the form of ax plus b. It's going to be something in that form, but how do we calculate what these a and b values are? X is going to remain that sort of unknown quantity. I just need to figure out what are a and b. Well, we're given formulas for b and a. And I will just take a moment to clarify here that actually in the statement here, the book used b as the slope and a as the y intercept here. So in order to remain consistent with the textbook and to remain consistent with the notes, I shall say a plus bx here. So once again, just to be super clear here, this best fit regression line, it's of the form a plus bx. This is similar to that mx plus b form that we talked about earlier on, where we have the slope, which is the number being multiplied by the x, and then we have the y intercept, which in this case is the a value. Slope is this b value here. And we have formulas for what the slope b and what the y intercept a are. And it's using the exact same notation as we saw earlier on when we had the formula for calculating the correlation coefficient between the two quantities x and y. We have n times sum of xy minus sum of x's times sum of y's, all divided by n times the sum of x squared minus the sum of x squared. That's our slope. And then our y-intercept, our a value, is the sum of the y's minus your b value that you found times the sum of the x's, and that's all divided by n. So you do have to find your slope first before you find your y intercept. In this video, I just wanted to introduce you to these formulas and just give you a little bit of background knowledge into what is actually going on here. In the next video, we are actually going to do some sample problems, and we are going to see how we calculate these things. So actually getting into the deeper end with these formulas and doing the work comes in our next video. Guys, if you have any questions or comments, please be sure to reach out to me. Emails, phone calls, postcards, texts, whatever. Otherwise, until the next video, take it easy, guys.